We looked a little at air-sea interactions when we did oceanic interseasonal variability and air-sea interactions that occur for the mesos and MJOs. We will revisit this in the context of coupled ocean-atmosphere feedbacks with some details. This is the same story we saw before. This is looking at day 0 when the rainfall is maximum over the eastern Indian Ocean before it crosses, before the MJO tries to cross over the maritime continent. We are looking at various fluxes and sea surface temperature. So sea surface temperature before the convection over the eastern Indian Ocean is warm. Convection cools it. There is a delay in the maximum cooling as it passes over, and then the SST reorganizes for the next event, or just going back to the background. There is the net heat flux, which is positive, warming the sea surface temperatures, and you can see the lag there between the net heat flux and sea surface temperatures, which gives you a sense of the ocean dynamics versus net heat flux in determining the SSTs, because there is also mixed layer dynamics involved in this, so it's not exactly a quadrature. The sensible heat flux is kind of low, short wave is high before the convection, clearer skies allowing more sunlight to come in. As convection arrives, rainfall arrives, cloudiness decreases the solar radiation, and then it goes back to being positive. There is the long wave, which is opposite of the short wave, as you can expect, and latent heat flux is positive, so calmer winds, less heat loss, warming the sea surface temperature as well. So you can expect that looking at the short wave and the net heat flux. And then latent heat flux goes negative, so ocean is losing heat as the winds with the convection pick up, and then back, and so on. We have looked at something like this before with the MJO convection, rising motion, divergence at the top, and subsidence on the front end and back, and we looked at how clearer skies ahead would allow more radiation to come in, weaker winds associated with the MJO convergence would reduce the latent heat flux and warm the sea surface temperature, so you have calmer ocean conditions and net heating, whereas behind it you have reduced solar, the anvil extending, and latent heat flux increasing because of the wind anomalies. Of course, Vichy used this easterlies and westerlies to argue that the background easterlies would be enhanced by the easterlies associated with MJOs, increasing heat loss from the ocean and charging the atmosphere with moisture, creating instability, moist static energy, and favor eastward propagation. But the argument here is that the actual air-sea interactions and fluxes from the ocean are potentially able to feed back a little to MJOs, but they are not a fundamental ingredient. Okay, so you can see that the SST cooling here is about 0.3 Kelvin, and warming here is about 0.3 Kelvin, but these are riding on very warm SSTs, so they are not that small in terms of their impact on the moisture dynamics and air-sea interactions and atmospheric response. People have looked at it. This is Charlotte Demotte's results, November to April 1986 to 2013, mean column water vapor in kilograms per meter squared, looking at reanalysis as the data for best estimate of observations. And this is the difference between a coupled GCMs and the several models, 4 models were analyzed, minus error, so you can see that the model has biases in zonal and meridional gradients, which are very critical for propagation of MJOs, especially across the maritime continent, and whether they get detoured here and so on, and they have interactions with the background Australian monsoon, etc. In the boreal fall-winter season. The uncoupled runs can be done by forcing with observed SSTs, in which case they would reduce the biases compared to the coupled model, because coupled models have biases in SST, which then becomes amplified in the coupled model. But one can also take SSTs from a coupled GCM itself and force the atmospheric model, in which case you may still get different biases compared to reanalysis, because the model biases are sometimes amplified when coupled. So coupled minus uncoupled shows here some pattern that is obviously going to impact, and this is in the region where detoured MJOs go through. So one has to be aware of how the detouring of MJOs around the maritime continent and propagation across is affected by coupled air-sea interactions. So the model biases make it tricky to explicitly extract MJO feedbacks or coupled feedbacks within MJO and ocean processes and how they feedback to the MJO. I'll say a bit more about that in the next podcast on El Nino. The ocean response is not just in terms of heat fluxes. Obviously, looking at the Argo data from this location in the Indian Ocean, which is very much in the MJO band, you can see that oceans can have complicated structures when you mix the heat flux forcing, wind forcing, as well as freshwater forcing. So you can get situations like this at this location, but also in the eastern Indian Ocean, where the haline stratification or salinity stratification is shallower than the temperature stratification. So the isothermal depth here is down to this 75 meters or so, whereas salinity is lower in the top 40 meters and then increases with depth. And the density that is well mixed corresponding to salinity and temperature is about 40 meters, and then there is a density stratification, but it's called, this isothermal layer below the mixed layer is called a barrier layer, because it acts as a barrier to cooling of the temperatures, sea surface temperatures, even if there is turbulent kinetic energy at the surface and mixing of waters from below. So it's kind of a decoupling of the dynamics and thermodynamics in that sense. So even if mixed layer gets deeper and water is entrained, sea surface temperatures are not going to cool as usual, what is generally expected with entrainment, because of this isothermal layer. So this can also make a difference to how MJO related convection and SSTs are going to be affected by the mixed layer structure. The ocean also has remote influences. So looking at this cartoon from PNNL, there is the eastward propagation, a deep convection situated over the Indian sector, and ahead of it you have the shallow cumulus congestus, which are argued to be critical for the heating and moistening the atmosphere with moist static energy, creating instabilities that create the eastward propagation. So you have upward warm moist air, downward cold dry air, and behind it also you have similar structures, but the cloud structures in detail are different. The deep convection and anvil or the stratus deck extends behind, whereas the ahead you have the forward bending two-day waves in general, and so on and so forth that we looked at. So the ocean response associated with the wind anomalies of the MJO deep convection can also create waves in the ocean, Kelvin waves and Rossby waves, and the waves, Kelvin wave travels eastward, can hit the coast of Sumatra and become coastal Kelvin waves, which you can see in both these figures. So this is showing the fraction of the standard deviation of sea surface height caused by MJOs. So sea surface height is an indicator of the thermocline depth. If thermocline deeper, sea level is higher. If thermocline is shallower, sea level is lower because of the relation with the thermal structure and the pressure gradients and so on. And you can see that 70% or so of the standard deviation can be explained by MJOs over here, and it's in the range of 40 to 50% over here. And the actual standard deviation in sea level in centimeters is shown here, a couple of centimeters, and you can clearly see the coastal Kelvin waves, which will be even clearer in the next picture. And you can also see the Rossby waves, and these Kelvin waves can go around and shed Rossby waves on this side and go around, become coastal Kelvin waves on the other side. And you have also the Kelvin waves going down here and pushing the thermocline down and becoming coastal Kelvin waves and so on, depending on how energetic they are. And we will see a little bit of that in the next podcast on El Nino and MJOs. Okay, so looking at composites of sea level for different phases of MJO, we are going from phase 1 through 8. 1 and 8 are in the Western Hemisphere when MJO convection is in the Western Hemisphere. 2 and 3 over the Indian Ocean. 4 and 5 maritime continents. 6 and 7 in the Western Central Pacific, and so on. And when it is negative here, we are at the interseasonal time scale, so deviation from something like the seasonal mean, then it's an upwelling Kelvin wave. You can clearly see the Kelvin wave going round and going down here, which also interacts with the Indonesian through flow coming out here and can create baroclinic and barotropic instabilities, which are released into Rossby waves, which go back to the southwestern Indian Ocean and affect the heat budget of the region where MJOs are typically born or re-energized after coming around from the Atlantic or the African continent into western Indian Ocean. So the question is whether the air-sea interactions and the associated heat fluxes are directly able to affect MJOs, or are they minor and can have a small feedback? In general, the conclusion seems to be that the coupling is definitely important for MJOs in terms of amplitude, propagation speeds, and so on. But these air-sea enthalpy fluxes, air-sea heat fluxes, don't seem to be that critical according to some arguments. But there are indirect effects of ocean that can happen, like cloud feedbacks, SST and cloud feedbacks, these large-scale convergences generated by SSTs, and also the fronts in SSTs, which can generate convergences and momentum entrainment from above, and so on. So the air-sea interactions at the fronts appear to penetrate deep into the troposphere and can have potentially indirect feedbacks as opposed to just direct feedbacks through air-sea interactions and heat fluxes. So again, it seems like I'm mostly raising questions, and that's because I'm trying to teach this course and I want to tell you what we know, but also tell you what we don't know. But there is a lot we know, and idealized models, observations, process models, and GCMs are all used to advance the understanding of MJOs so that we can improve the simulations, predictions, and projections. Okay, so we will look at the El Nino MJO interaction in the next podcast.